Hello, pre-calculus. I will be working through pages 18, 19, and 20 in this video. There will be a quiz posted through the TED-Ed site. That quiz, I will make that quiz due by, let's make it due by the end of the day, Monday. It's just 3 questions. We are working steadily through the polynomials unit. I will not be doing all of these. I will be doing some. You should go through and practice on your own. The solutions to this in PDF format will be posted and attached to this video through the Google Classroom. The originals, again, are posted in the original Intro to Polynomials link in the Google Classroom. This is page, again, 18, 19, and 20. Okay, so we're going to sketch functions. Polynomial functions. Linear function is definitely a polynomial function. Sketch this quickly for the heck of it. It is a 1-degree function. It has one root of multiplicity 1. If I set it equal to 0 and I solve for x, so x equals 1, so that's a root. Now in this case, we do need to consider, remember y equals mx plus b, because we need another coordinate to go off of, or we could just use the slope. So in this case, we just rise 1, run 1, all that good stuff. Let's get the y-intercept. When I plug in 0 for x, I get y equals 0 minus 1. So the y-intercept is -1, and it also connects with our slope. We rise 1, run 1, or we fall down and run backward. And that's it. Okay, good enough. And I'm going to label this equation y equals x minus 1, 1 degree, 1 root of multiplicity 1. This is a 2-degree polynomial. Each root has its own multiplicity. So the degree is for the entire polynomial, poly for short. The multiplicity is for the root. So this is, and when I say the multiplicity, imagine exponents here. The x in here is raised to the first power. Each root or factor is raised to the first power. Each of these roots, there's 1, 2, 3 roots, are all of multiplicity 1, yet the entire polynomial is of degree 3, 1 plus 3. So far, all of these are of multiplicity 1. This is a situation where this root is of multiplicity 2. This root is of multiplicity 1. This root is of multiplicity 3. If I add them all up, 3, 4, 5, 6, this is a 6-degree polynomial. From the little bit of work you did in the last video, I hope you have some idea of what even degree polynomials look like versus odd degrees. The odd polynomials, y equals 1. You also have cubic polynomials, centric, septic, whatever you would say for 9. Generally, they're odd. They start over here on the left and they work their way up unless there's something to flip them. Even degree polynomials are all rooted in your first even degree parent function, the quadratic, x squared. X to the 4th hugs the curve a bit longer. X to the 6th hugs the curve even longer. So whether or not the degree is even or odd has a lot to do with the overall shape of the function. Right now, this is even. I'm going to go ahead and skip this. You guys have this. I'm going to do y sub 3. If you want to, I suggest go ahead and do y sub 2 and then maybe check your work to make sure you have it. But what I'm going to do is I'm going to plot each of the roots. Remember, we set each root equal to 0, so x minus 1 equals 0. So one root is at 1, -2. And then for some students who are still maybe confused, when I set that equal to 0 and I solve for x, x equals +3. That's why I'm going the opposite way. Again, we're in parentheses here. And again, that has a lot to do with why we go opposite. So I'm going to go 1, 2, 3. Now, each root's of multiplicity 1. The entire polynomial is of degree 3. it's odd, so I'm going to use this as my benchmark. It's odd. There's no negative signs in front of the x's, so I know I start somewhere down here and I go up. Without knowing even my y-intercept, I know I have to come back because there's a root here. Think about center of gravity. The moon rotates around us, but it's not going to fly off into space because it's drawn to the earth. So no matter how high up or far away I go, I have to come back here. I have to come back here. And it definitely looks like one of these, except the roots are spaced out. I'm going to go ahead and try to find my y-intercept just to add a bit more detail to my solution. To find the y-intercept, I'm going to plug in 0 for all the x's. 0 minus 1 times 0 plus 2 times 0 minus 3. So for my coordinate x is 0, so what is y when x is 0? Y equals -1 times 2 times -3. -1, -2, -2 times -3 equals +6. So my y-intercept is at +6. 0, +6, 5, 6. So I'm going to change that. But you see, even though we didn't know the y-intercept, we were pretty close just by going based off the gravitational pull, if you will, of the roots. And that's a very quick, even sketch of a polynomial function. We have the roots. If you want to, you can label the roots. X equals 3. Let's label this 0, 6. Let's label this x equals -2. And then this is, I'm going to use a little arrow. X equals +1. And remember, the graph is the same thing as a function. Good deal, good deal, good deal. So I'm going to work this one out. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, and this one out. I'm going to leave y sub 4 for you to do on your own and check. I suggest you sort of pause the video and try to do this on your own. I'm also going to leave it for you to write out in your own words what's happening. It's very important to write in your own words what's happening. That helps the learning make sense to you. It helps you review. The responses will be, again, posted in the solutions. But let me start off with this fifth term, y sub 5. Initially, all multiplicity is 1. Notice I counted. I wanted to make sure I did an odd one and an even one. 4, 5. This is a degree 5 polynomial. So it will look something like this. It's going to hug the curve more. It's going to look something like that because it's an odd degree. Let me plot my roots. +1, -2, +3, -4, +5. I'm going to go ahead and get my y-intercept since I'm here anyway. So y equals -1 times 2 times -3 times 4 times -5. That's -2 times -12 times -5, +24 times -5. It's negative, what's that, 120, I think? I'm going to get my calculator just to make sure. I think it's -120. Okay, yep, just making sure. So my y-intercept is 0, -120. So it's a really high or really low y-intercept. So I'm just going to estimate where it is. Based off of this graph, it's just going to be, I'm going to put some dot way down here, just for the heck of it. Because we're just doing a quick light sketch, just like sketches in art. It's not super detailed, but it gives us enough of a picture so we know what it is. A sketch of a cat will look different than a sketch of a pill bottle. We just want to know generally what it is, and that's the same thing when I talk about sketches here. Let me have the nerve to label this just to remind myself what it is I'm doing. Okay, so because it's odd degree, I'm going to start way down here. I'm going through this root. I have to come back down here. And you know what? Now I have to hit up the y-intercept because I'm crossing this line in order to get that root. So I have to go down here somehow, somewhere, bam. There we go, we hit the y-intercept. Now we have to, so you can tell this is a very steep line. It's traveling 120 units in like 1 unit. Now we're coming through here. Now we're off here. There we go. And ultimately, it still has the same shape. It's still, let's get that right. It still starts here and ends here. It just does a lot of weird stuff on the side. I'm gonna go through and graph this in Desmos graphing calculator. Okay, so let me share the screen. Okay. So let's type this equation in. I don't think I need the y equals, but let's type it in anyway. X minus 1, x plus 2. X minus 5. And we can see on our screen right now, it's looking a lot like what we had. Let's zoom out a bit. Okay, so I'm gonna edit this, have to edit it somewhat slightly. So let's make the y values very narrow. There's a lot that goes on between positive and negative 5. So let's just make this like 9. And let's make this negative 10. Okay. Oh, sorry, my mistake. This is actually, I changed my y's. We're gonna have to make this positive 80, and then the y is gonna have to be negative 150. And my x's are the ones I should have changed. Okay. That's more like it. So we can see we started down here. We had to go way up to the top here. We had to go way down here. You can see our y-intercept is 0, negative 120. These are our roots. Okay. And these are all, this is a relative maximum, a relative minimum, a relative maximum, a relative minimum. Changing and augmenting this shape augments the other shapes. If I throw in an a, let's say I multiply everything by 5, notice it gets stretched out. If I multiply everything by 0.5, it gets flattened down. Again, when we would be doing roller coasters, this is one of the things we would be doing to do roller coasters. I could lift it up a bit here, I can change it, but we're going up, boom, boom. This one, obviously, knowing a little bit of physics, wouldn't work. You would have to stretch this out a bit more, stretch the roots out, things like that, but such is life. Well, it wouldn't, you wouldn't make it out of this, let's just say that. Yeah. So let's go back to doing the next practice problem, shall we? So now let's go here. Again, a sketch. We didn't pick up on this really high leap here, but we still got the gist of it. We go down a lot relative to these roots. There is something too, if this is so far down, generally speaking, we will go way up here. But we're not concerned with that much detail because we have graphing calculators and Desmos graphing calculator. We just want to get the general gist of, we still got the general shape. So let's go here, y sub 6, or the 6th graph. Again, the first step, check multiplicities, they're all multiplicity 1. The second step, recognize what is the degree and is it odd or even? 1, 2, 3, 4, 5, 6 roots. So if it's of degree 6, it has 6 roots. It's even, it's gonna look something like that. Third step, plot all your roots. Fourth step, plot your y-intercept. Fifth step, graph. 1, let me just do all the 1, 2, 3, 5, okay, a -2, -4, -6. And let's calculate the y-intercept. -1 times 2 times -3 times 4 times -5 times 6. And I'm getting a huge number, -720. So my y-intercept is 0, -720. Very long leaps and bounds, but we're just going to do something like that we did there. Okay. It's even, so we're going to have to start up here someplace, and we're also going to end here. So maybe if you want to draw the little arrows, we're starting here, we're going to end here. So here, I'm going to go down, hit this root. I have to come back, gravitational pull. Maybe if you know it's -720, maybe you want to go way down just for exaggeration purposes, way up, way down, somewhere here, 0, -720. Okay. Then we want to head back up, way up, way down, way up. And look at that, we ended up in the arrow. Crazy graph, but we still can manage it if we just focus on the y-intercept and the roots. That's the importance of the roots. There's a lot going on here, but we still have the essence. We know where it starts, where it ends. We have the roots. If you can't get the whole system, get components of the system, and you'd be shocked where that can take you. I'm going to go to Desmos to graph this. -1 plus 2. Okay, so they're just adding on. 5, x plus 6. Yeah. Let me adjust that a bit more now. Okay, and you can see something. It does look reminiscent. 0, -720. In this case, these doubled over. Notice the symmetry in it all too. It's fascinating thing with the symmetry. The roots weren't necessarily evenly spaced apart. It's not like it was 2 to the left, 2 to the right, but we still got some semblance of symmetry going on. And here we have all the roots. If you had your calculator and you wanted to calculate, say, the relative maximum, you would just find the relative maximum here. I will go and show you how to do that in the calculator next. So I'm going to calculate one of the relative maximums. Actually, I'm going to do myself a favor. I could do it. It's just a lot of values, but I'll just zoom out. I think it'll be okay. Okay, so x minus 1, x plus 2, x minus 3, x plus 4, x minus 5, x plus 6. Just hit graph and see what we're dealing with. Some crazy stuff. You do generally have to see the maximum in the screen, so I'm going to just do an automatic zoom fit just to see if it'll get me somewhere near so I don't have to do so much augmenting in the windows. Yeah, that's not helping me either. A lot of crazy stuff going on here. Let me go to my windows and change my Y. Wow, okay, 846,000. Let's just do, I'm not doing 46,000. Let's do 10,000 and see what we get. Okay, that's doable. Okay, luck of the draw. Let's find this relative maximum. There is no overall maximum or minimum. It's only now relative minimum, relative minimum, relative minimum, relative maximum, relative maximum. 2 relative maximums, 3 relative minimums. Second calc, maximum. I'm going to now find this maximum only because my cursor is obscured by this, and you can more clearly see this maximum, so I'm going to switch to this one. Hello, Harrison. That's my cat, Harrison. So left bound, right bound, guess. Yeah. And that's the relative maximum when x is 2.09, y is 581. Hooray. Okay. On to page 18. Here we're going to sketch graphs. We're going to be less bounded. I'm just going to draw my own lines. And we're going to have to deal with multiplicities of things other than 1 this time. This is a nice cubic. You should be able to do that. We've done similar things. But I'm going to do this of multiplicity 2, multiplicity 1, multiplicity 1. Overall, it's of degree 2, 3, 4. So this is a degree 4 polynomial. It's going to look something like this, something along the lines like that. And let's talk about multiplicities. An even multiplicity we call a bounce point. An even multiplicity bounce point. So let's say we have a root x minus 1 squared. That means there's a root at x minus 1, but it bounces up. So whatever's going on is going to hit here and like a ball bounce up. Notice, and that's how we describe multiplicities too. When you've ever seen a quadratic equation, let's talk about the parent function y equals x squared. It is of degree 2, therefore it has to have 2 solutions. In this case, the solution is x equals 0, and 0 is of multiplicity 2, which means it hits it and bounces up. So it has 2 solutions, it's just of multiplicity 2. Let's talk about odd multiplicity. These are called pass-through points. Let's do something. Let's do x cubed, the other parent function, x cubed. It has a root at 0, and that root at 0 is of multiplicity 3. So it hits it, slides through, passes through, goes through. That's multiplicity 3. Something of multiplicity 1 still passes through. It just doesn't slide through, it goes straight through. So the more odd, the higher your odd multiplicity, the more it hugs the root as it passes through. And that's what we're going to do for multiplicities. All that good stuff. I'll leave this if you want to take a screenshot or run it. Well, you can pause the video and all that good stuff. So let's plot these points. The first steps are still the same steps. We know it's degree 4. We recognize the multiplicities. Let's plot the points. We have a point at -2. We have a point at +1. We have a point at +3. I'm going to go ahead and get my Y-intercept as well. Okay, so my Y-intercept when x is 0, that's 2 squared. So 2 squared is 4 times -1 times -3, because in this case, when I plug in 0 for x, I'm just multiplying what I have. So my Y-intercept is something about 0, +12. So now it's even, so I have to start here. That's why it's important to recognize if it's even or odd degree, 1, 2, 3, 4, and that tells me where I'm starting and where I'm ending. I come here, -2 is a bounce point, so I have to bounce back up. And if I didn't bounce back up, I wouldn't get this Y-intercept. -1's passed through, so I'm passing through. And whatever's going on, I'm gonna have to come back up, pass through here. And if you zoom in, multiplicity 2, it looks a little bit like a quadratic. Multiplicity 1 looks a little bit like a straight line. Multiplicity 1 looks a bit like a straight line if you just zoom in and look at what's going on directly around the roots. I'm zooming in for the heck of it. Let's see how far this can zoom in. Yeah. So multiplicity 2 looks a bit like a quadratic, looks a bit like simply straight lines. We have the roots, smooth flowing curves, because notice, even if your calculator looks like it's sharp, everything curves that way because it's being stretched and pulled in a direction, but it's not hammered in that direction, if that makes sense. It's about influence of points veering you off of your guideposts. Okay. And I'm going to do this one because it's an odd multiplicity. And I'm going to do y sub 5. Follow along, please. Do this with me. And then I'll let you do y sub 3 and y sub 6 and check your work. Again, the answers are attached. So let's start off with y sub 4, or the fourth graph. Again, this is page 19. Okay. 3, 4, 5, 6 is degree 6. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. I'm actually going to jump and do y sub 6. This is degree 6. This is an even degree, 4, 5, 6, 7, 8. This is 5, 6, 7, 8, 9, 10. No, I'm going to jump and do y sub 3. 1, 2, 3, 4, 5. I'm going to jump and do y sub 3 because I want to do one with an odd degree just for the practice. 5, 6, 7, 8, yeah. So instead of doing y sub 6 in this, I'm just going to do y sub 3. But you should be doing all of these anyway. You should be pausing it. But I'm still going to jump and do y sub 4 since that's what we started, and then I'll go back and do y sub 3. So the degree is 6. It's even, something along those lines. -2, +1, +3. Starting up here, I'm going to end up here. Let me calculate my y-intercept so I could plot that point. It's helpful. 2 squared is 4 times -1 times -3 squared is -20, or -3 raised to the third power is -27. Just so you believe me. Good job. Times -4. So we have positive 108 for our y-intercept. So just some value way up here. I'm going to even have the gall to put it way up here someplace. So we're going to come down. There's a bounce point here, so I'm going to bounce up, hit this value, pass through here at 1, make it sort of try to make it look like a straight line, but it's not that deep if it doesn't. And then going through 3, it's an odd multiplicity, but it's not multiplicity 1, it's multiplicity 3, so it's going to look more like a cubic function as we come back. So I'm going to sort of just slide on through like that, something like that. And of course, check your Desmos graphing calculators to verify these. I'm going to do y sub 3 now, and then I'll go type these into Desmos just so we can see them. Let's jump into y sub 3 now. 1, 2, 3, 4. 1, 2, 3, 4. So I have a root at -2, a root at +1, and a root at +3. The degree is 1, 2, 3, 4, 5. It's a degree 5 polynomial, so I'm going to start down here somewhere, and I'm going to end up here somewhere. Let me get my y-intercept. 4 times -1 squared is +1 times -3. So my y-intercept is now at -12. 4, +1, -3. Some value down here, 0, -12. I'm going to come through. -2 is a bounce point. -1 is also a bounce point, so I'm going to come here, bounce off. And then 3 is a pass-through point, so I'm going to come through here. And that's approximately what that graph looks like. If I want to label my solutions, And you can look and see bounce, bounce, pass through point. Let's type y sub 3 and y sub 4 in Desmos, and then we'll move on to page 20. Okay. X plus 2 squared, x minus 1 squared. You can even see how it's augmenting and changing x minus 3. And then let's get rid of the others. Okay. Zooming in a bit. I'm gonna have to change this a bit now. Okay, that's a lot better. So we have our y-intercept at 0, negative 12, bounce, bounce, pass through. That's y sub 3. Now let's do y sub 4, I mean. X plus 2 squared, x minus 1, multiplicity 1. You can put 1 here, it doesn't matter. X minus 3 cubed. So notice how the roots are the same and it hits at the same spot. It just bounces different. It's also even. So it ends up here. So we're coming down here, bounce, pass through at 1, and notice it looks more cubic because it's raised to the 3rd power instead of the 1st power. If this was raised to the 5th power, it will look more cubic exaggerated. That's what it is. It hugs it more. That's why it's so important. I hope you did those, the page 17 and 16 to know what happens as you increase powers. Okay, so the answers for y sub 5 and y sub 6 are posted. Check those. Again, tutoring's every day except Thursdays. It's only a half hour. So Monday through Friday, 3 to 4. Thursdays, tutoring's 3:35 to 4 if you have questions. Okay. I would expect a test on polynomials sometime around May 8th because you can see we're steamrolling through the contents. So here I'm going to practice writing equations. And the quiz posted in the TED-Ed link, you're going to have to type in equations. Type them in as best you can. For example, if you have to type in x minus 2, use that little caret 2 to indicate a multiplicity of 2, and then use your parentheses, x plus 3, caret 3. You're going to have to type them in that way. I'm sure you can figure it out. Okay, so let's start off with number 1. Then I'm going to jump and do 3 and 4. 2, I think you can figure it out. Write the equation of a polynomial. Notice they say a polynomial. There are going to be a lot of correct answers. Satisfying each set of given conditions. If it's impossible, briefly explain why. In many cases, there are an infinite number of possibilities. First degree polynomial, which crosses the x-axis at x equals 3. So if it's at x equals 3 and I solve for 0, I get x minus 3 equals 0. So this is the solution. Let's do y equals x minus 3. It's first degree, crosses the x-axis at 3. I think that's the only way of doing that one. There's only one solution there. Let's look at 1b. First degree polynomial bounces off the x-axis. Is that possible? No, not possible. Because if it bounces, that means it's of multiplicity 2. But you can't have multiplicity 2 with just 1 degree. It's impossible. Does not touch the x-axis. First degree polynomial. Let's do a sketch. Any diagonal line would touch the x-axis, so it would have to be parallel. If we have a parallel line, the equation would be y equals some number, some constant term. For example, y equals 10. Now, is y equals 10 a polynomial? No, it's just a constant term. Y equals 10 isn't a polynomial, it's just 10. Graph the line 10. Graph the line y equals 5. Um, so this is not possible. What is this that keeps calling me? Okay. Not possible. It's number one. That's it. Forces you to think about what's going on. I highly suggest you try to do two on your own and then check the answer and the answers provided. I like these problems because it forces you to think about what is and what isn't, what is possible and what's not possible. So let's now jump into 3. Hopefully you paused and did number 2. Okay. Cubic polynomial crosses the x-axis at these points. So y equals x plus 1 times x plus 4 times x minus 3, all multiplicity 1, because 1, 2, 3, it's cubic. That's it. Um, in this case, I think that's the only one because it has to cross at those specific points. Let's jump into B. Bounces off the x-axis at x equals 2. First, so what I'm going to do is I'm just going to set up my roots. X minus 2 times x plus 3. It's cubic, so it needs to be of degree 3. Bounces, it has to be even and passes through. This, I think, is the only answer because it has to be cubic. That's our constraint. 1, 2, 3. If this was 4, yes, it would bounce, but we would be left with a degree 5 polynomial, which won't satisfy this cubic situation. Passes through x equals 4, no other zeros. Y equals x minus 4. Pass through, this works. 3 is odd, so it will pass through it. So we can have a multiplicity 3, so it passes through this root. No other zeros, and it's cubic. There you go. Now, if they said bounce, it wouldn't work because it'll have to be even. Does not touch the x-axis. Let's think about this, sketch a few examples. No matter what you do, even if I flipped it around, that little tail is always going to go off towards infinity, and it's always going to have to hit the x-axis. So I don't think this is possible. We know this is possible, right? Yeah, but this isn't possible because that little tail. Okay, this is fun. On to number 4. Quadratic polynomial which crosses the x-axis at, or I'm sorry, not quadratic, quartic. Quartic, that's 4, quarter. So that means it's of degree 4. Okay. Okay, crosses the x-axis at, ooh, look at all these points. But I see 1, 2, 3, 4 zeros, quartic 4. So I'm thinking y equals x plus 2. I'm just going to put in x times x minus 3 times x minus 7. Typically, this x would be out in front, so we notice it. There's no need to do x minus 0, x plus 0. All multiplicity 1, and that's how we would do a root at 0. It's just x. It's not x plus or minus. X isn't moved left or right. It just is at the origin. Okay. Bounces off the x-axis at x equals negative 2 and x equals 3. Okay. Again, let me just set up my zeros. X plus 2, x minus 3. Has to be degree 4. bounces off the x-axis at this and that. So they have to both be raised to the second power. 1, 2, 3, 4, bounce point, bounce point. Look at that. Okay. Bounces off the x-axis at, okay, this is getting boring at this point. I think we got this. Does not touch, let's just jump down to E. Do the rest and check your answers. I'm going to do this one. I'm going to do D because D is a little bit more of a challenge. Um, if in doubt, always start off with your roots, and that gets you started. Passes through this and that, no other zeros. So it has to be 2 pass through. Let's think about what 2 odd numbers sum up to. 4. This could be 1 and this could be 3. That's one correct answer. There's multiple correct answers. This could be 3 and this could be 1. If we label one 5, we're no longer a degree 4. There is no degree 0, 0. You don't have x, you just have a constant term, y equals a number. 2 won't work because 2 would be bouncing. So those are the 2 options there. Does not touch the x-axis, it's even. You can have all kinds of weird stuff going on, and all of it's just floating up above the x-axis, a bunch of imaginary numbers, because they're floating up above the x-axis. So that is possible. Oh, let's write the equation of this, though. Does not touch the x-axis. Oh, this is fun. E. We have to write the equation of one that doesn't touch the x-axis. So we are going to need to get imaginary numbers in order for this to happen. Which means when I solve for a root, I'm going to have to solve for, I'm going to have to end up getting a negative number. And I'm having to square it. So let's think a bit about this. There's several approaches we can take to this. I can start off with an outright imaginary number. That is possible. If we're thinking about roots, x equals 5, okay. Well, what if instead I have x equals 5i? If I'm graphing this, remember a plus bi or x plus yi, where this is my horizontal displacement, my vertical displacement, so I don't move left or right at all. In this case, complex numbers do have to be positive and negative. I go up 5i, or I go up 5, I go down 5. Those are my imaginary roots. So it's possible I could have x simply equaling 5i or something along those lines. Take some time, try your best, and come up with your own solutions and see what works, if anything works. There's another way to go about this in terms of writing without having to completely interject I as a solution. There's actually several ways to interject I as a solution. Let's think about it this way. What if we outright write the equation y equals x raised to the 4th power plus any number, let's call it 5. And what if I told you to solve for y? We essentially set it equal to 0 and solve for this value. I would have, let me get my little trusty notepad out. So again, we have y equals x to the 4th plus 5. And if I replace y with 0, and I want to solve for x to get the solution, I would have negative 5 equals x to the 4th. I would take the 4th root of both sides. You can take the cube root of a negative number and it's fine, because negative 1 cubed is negative 1. The whole point is you cannot take an even root, whether it be 2 or 4 or 6 or 8 or 10. Let's try this out. We have the square root of 5. Our calculator freaks out. Non-real number. let's try the fourth root. So I'm going to do 4 math fourth roots, -5. Our calculator still freaks out because it's even. It's in this case, 4 identical numbers that multiply to get -5. That's not happening ever. So I'm still going to have something along the lines of some imaginary number that's just not possible. However, our degree is still 4. Therefore, it's floating. Let's graph this in Desmos because I'm curious to see what this would look like. Um, x to the 4th plus 5. Okay, we got that basic, simple looking. Oh, +5 plus c, we're just lifting it up above the curve. Doesn't cross the x-axis, but it's degree 4. Look at that, look at that, look at that, right? That's why it's also good to know what changing A, B, and C does. So those of you guys that skipped it, you did yourself a disservice. So generally speaking, going back to the solution, a general answer would be y equals x to the 4th plus a. And a could be any constant term you want. Even better, let's make this a c, just because c for constant. And that's an easy way. It's obviously quartic. It has 4 imaginary solutions. They come in pairs. Whatever those imaginary solutions would be, they come in pairs. In this case, the 4th root of -5 has 4 solutions because it's 4 numbers 4 identical numbers multiplied by each other, whatever they may be. It's just that they're imaginary solutions. So that's E. Looking at E and thinking about E, I thought of another way even to do D. Because as you're working math, you sort of get your juices going and all of that, and then you figure out new and profound and interesting ways to solve things. So let's look at another way to do D. Since you're here, I hope you paused and did this on your own. I'm going to go ahead and give this answer to you. Just so if you don't want to have to check the attached link, you don't have to. Yeah. Bounces here, pass through, that's the only way. But let's look at another way to do D. D is a pass-through point. Yeah. D is a pass-through point, and then you have another pass-through point, but it has to also be a quartic function. So another way of writing this could simply be y equals x plus 1 times x minus 5 times, we're going to use that trick we used in the last one, 1, 1, this has to be x squared plus some constant term, whatever that term is. It could be 10, it could be 20. One solution pass through, one solution pass through. This adds 2 more roots, so we have a quartic function, but they're floating, so they don't cross the x-axis. These wouldn't be necessarily considered pass-through or bounce points. They're just raw solutions. So that's another way to do D. Check your answers. I'm going to do another video for 21 and 22, but you have enough to hopefully be successful in the attached quiz. Take care. See you on the next lesson. Have a good day.